Hi, everyone. Welcome to my review session. So kind of like how I mentioned in class, my name's Allison, again, if anyone forgot. Feel free to call me Allison the whole semester. I'm not a doctor yet, and I'm not a professor, so Allison is great. But for my review sessions, usually I like to hold these just so we can go over practice problems, right? You'll have class Monday, Wednesday, then we can do a review session Wednesday afternoon. But these are just to help you ask questions and then we can kind of talk about it and then practice it together. I really believe that one of the best ways to learn chemistry is through practice problems. So that's how I kind of structure my questions. But I like to get feedback from y'all. So whatever you're uncomfortable with in the class, whatever you need more help with, that's what I like to tailor it to. So I always ask you what you want to do at the beginning of class. All of these are going to be recorded and posted on, not on Facebook, on Canvas, and then they're uploaded to YouTube as well. So if you find my YouTube channel, or like you'll see the YouTube video if you watch it, all of my past videos, I've been doing this for 4 years now, all of my past videos are there as well. So I've done 120 for Dr. Lindahl before. So any of those videos are there if you need something else. And then like if you need a refresher on Chem 107 or anything, Chem 119, I have videos from back there as well. Any questions for me about 120 or chemistry in general? No? Okay. I usually do this on my iPad. It'll be projected on the screen. I just definitely forgot my Apple Pencil in my other bag. So we're gonna do it old school method today. With that, what do you want to see today? What questions do you have? We can do lecture stuff, homework stuff, anything you want to see. You just want me to give you some practice problems, kind of a little review session or something from last semester.
Could you do like some stuff from, I guess, like the properties of solutions?
Yeah. Yep. I don't think I have access to your Alex yet. But if you have, so if you have like if you can read me a question or something, I can do something similar.
This one is kind of confusing. It's on like talking about the relationship between Coulomb's law, I think at least.
Okay.
Where it's hydration enthalpy and what is it? Hydration enthalpy and something. I wrote it down somewhere. And charge density, sorry.
Charge.
Hydrogen enthalpy and charge density.
Is there a question that you're looking at?
Question 3, it says some ions are sketched below, rank them in an increasing order of size of hydration enthalpy. That is like 1, blah blah blah. So it just shows 4 different ions, one like slightly smaller with a -2 charge, and then
Okay.
I can show it.
Yeah. So the question he's looking at has, does anyone know what question he's looking at? Start looking at. So what we're looking at is different charges and different sizes of charges. So all of these are negative, which is going to be on the left-hand side or the right-hand side of the periodic table. Where are anions? The right-hand side. Yep. So we can have something like fluorine minus, we can do oxygen 2 minus. Or we can have chlorine minus, and then we can have sulfur 2 minus. All right, here's just actual examples of things that will have the charges listed. All right, so you have a -1, a -1, or a -2, a -1, and a -2. What do we remember about our periodic trends? As we go across the periodic table, what happens to our size of our atom? As we go left to right. It decreases, right? It gets smaller. So fluorine, as we go this way, our atomic radius decreases. What happens as we go down the periodic table from top to bottom, what happens to our atomic radius? It increases, yep, so. Atomic radius. Right, and this has to do with the shells and how many electrons are in that shell. So as we look at this second period of what oxygen and fluorine is, right, we have all of our electrons are being added to the same outer shell, but we have more protons to the center, more electrons to the outside. That's going to pull them all closer together. And so fluorine is going to be your smallest. However, when we look at sulfur and chlorine, here we have a whole extra outer shell that we're looking at. So this one has its nucleus and two shells. And then for your third period, you have 3 outer shells. That is looking at it, okay? So when looking at those pictures, you can kind of think of like, what atoms am I actually looking at? So we have a -1, a -2, and then in the row down, a -1 and a -2. So which ones are going to be the bigger ones in those pictures that you're looking at for? Would the bigger minor 2 be oxygen or sulfur? It would be sulfur, right? So this is going to be your largest picture in that homework question. And then which one's going to be your smallest? The -1, right? Your fluorine's going to be your smallest picture. Okay. And then what does it mean for the hydrogen enthalpy? What is that question asking?
Enthalpy occurs after the lattice.
Yep. So it has to deal with like the charge. Let me get you a real. What is it? It asks for the hydrogen enthalpy, right?
Yeah.
Hydration enthalpy, that's what it is.
This is saturate typical gas molecule.
So it is referred to as the change in enthalpy when 1 mole of gaseous ion under a standard condition of 1 bar pressure dissolves in a sufficient amount of water to form an infinitely dilute solution, which means that, right, you have a lot of water and not a lot of ions, right? Super dilute. So it's considered as the enthalpy of solvation. So hydration enthalpy. Equals enthalpy of solvation, right? So if you see any one of these words, that's what that's going to mean. And as you get smaller atoms have higher hydration enthalpy. So if we're looking at between the difference between fluorine and chlorine, which one's going to have the higher hydration enthalpy? The fluorine's going to have the higher hydration enthalpy because it's smaller, right? So it can fit in more pores. Right. Think about a dilute solution. You want to minimize that as much as possible. So the smaller the atom is, the more it's going to be able to, the easier it's going to be dissolved. And then I believe, I'm just looking at my notes. It has to deal with the solubility, right? So they're going to be smaller. So if you think about atoms, right? An atom being able to, right? You have in water, you have right, you have your water molecules here. So in water, when you're dissolving, it's going to form that pocket around all of the atoms. So if you have a smaller atom, then you're able to make those molecules closer to each other. And then it like kind of disappears, right? Because it's fully dissolving it. So the smaller it is, the more the water can surround it more easily. So it's just easier dissolved. Okay, and then this is not telling me anything about charges, so that's good. In all honesty, this is not that important. This for your homework, it's important, but for the grand scheme of chemistry, it's not that important, so I don't use a lot about it. So it's just saying that the smaller the atom, the greater the hydration enthalpy. So if we look at the 4 that were given here, right, it doesn't really matter what the charge is, it just depends on the size. So fluorine is going to be our smallest atom. So whatever your smallest atom is going to have the highest hydration enthalpy. Right, and this is just because it's more easily dissolved. So it doesn't matter if it's +2, -2, it doesn't matter if it's +1 or -1, right? As long as it's the smallest, it's going to have the highest hydration enthalpy. So even if we look at right, if you look at lithium, magnesium, oxygen, and fluorine, which one's our smallest out of this one? Fluorine's still our smallest, so this one's going to have our highest hydration enthalpy. If we look at right, if we look at these 3, we have sodium, magnesium, and aluminum. Which one's our smallest out of this one? Aluminum's your smallest, and so this means that your aluminum, even though it's positive, it's still gonna have, right, water's polar, there's a positive end and a negative end. So this smaller positive ion is gonna be the most soluble or have the highest hydration enthalpy. Does that make sense? Does that help your homework question? And then this is not that important. Yeah, the most important thing to know with like hydration enthalpy is that likes are dissolving likes. So polar molecules dissolve polar things. When you have an ionic substance, right, is an ionic substance polar? Do we usually classify ionic substances as polar or non-polar? I guess is my better question. So if we look at hydrogen and oxygen, is this covalent or ionic? This is covalent. And then since it's covalent, we're sharing our electrons. Is this a polar compound or a non-polar compound? It's polar. Why is it polar? What causes? It's sharing. And what causes polarity? Change in electronegativity. Which one's more electronegative, the oxygen or the hydrogen? The oxygen. So does that mean that's going to pull the electrons closer to the oxygen or the hydrogen? The oxygen, right? So if we have more electrons, electrons are negatively charged, right? So that gives us our partial negative and our partial positive. So we have that dipole pointing towards that more negative, or that towards that more electronegative atom. What do we notice about the charges? Are they full charges or are they positive charges? Or are they partial charges? They're partial, right? They don't have a full charge, they have a partial charge. What if we look at sodium and chloride? If we were to break this up, what does that break into? What does sodium become? Na plus. And what does chlorine become? Cl minus. Are those partial charges or full charges? They're full charges. Are the electrons being shared or transferred? They're being transferred. That's because this bond is so polar, right? They can no longer share them. There's such a difference in electronegativity that the chlorine pulls all of that electron from the sodium and gives it to itself, right? Sodium is so electropositive, right? It doesn't want the electron. It gives its electron to chlorine. So an ionic substance is technically very, very polar because it's so polar, we're not even sharing anymore. Does that make sense? So in an ionic substance, that's going to be very easily dissolved in something that's polar like water, because water is also a polar substance. So that's important for like solubility stuff. Does that make sense of why that's dissolving? Right, if we look at something like, what's going to dissolve in? We can dissolve in we can dissolve in, we'll just say, we'll dissolve in ethane, which is this molecule here. Right, if we have ethane, is this a nonpolar or polar compound? It's nonpolar, right? Hydrogen and carbon have no difference in electronegativity, so this overall is nonpolar. So is your sodium chloride going to dissolve in your ethane? No, right, because this is nonpolar and this is polar. Right, water is not going to dissolve in ethane because water is polar and ethane is nonpolar. Right, oil is nonpolar, so that's why oil and water don't mix. So something like oxygen, right, where it's just two oxygen molecules would dissolve in ethane because a nonpolar and a nonpolar can dissolve each other. Okay, does that make sense for solubility stuff? Any questions on polarity and how we find that? Yeah.
Specifically for like alcohols,
Mhm.
if you're able to like augment the R group or something like that, can you change if an alcohol is more or less
Polar? Yeah, absolutely. So when we look at alcohols, right, usually have like methanol is this here. We don't have a very long carbon chain, and so this overall is going to be pretty polar, because we have this OH group, right? The C to OH is going to cause some sort of polarity difference. It's not great here. It's not a very polar molecule, but it is pretty polar. You can have propanol, which is 3 C's. Right, those all have H's at the very end. So as we extend our carbon chain, we decrease the effect that this OH group has on it, right? So the longer that chain is, the more nonpolar it gets. And then, right, to a certain point, I think it's like butanol is right still polar, and then everything after that is pretty nonpolar. So the left-hand side changes by your carbon chain. You can also put something at the very end here, right? Maybe change something that is polar. So you have a polar molecule and a polar molecule over here, and that would help your polarity as well. Any other questions? Yeah, absolutely.
It's one of the Alex questions. It's talking about Henry's law.
Mhm.
It says at 25 degrees Celsius, the Henry's law constant for dinitrogen monoxide, gas and water is 0.025 mole per atmosphere. Calculate the mass in grams of N2O gas that can dissolve in 1,100,000 milliliters of water at 25 degrees.
Okay, cool. So the important thing to note there is Henry's law. So what is Henry's law?
V equals HK is like a constant
Mhm.
pressure.
So we have C equal to K H, right? I think is Henry's constant times the pressure. Right, is that correct? I'm right next to you. And what does C stand for? Yeah, kind of. Yep. And so this is going to be your concentration of dissolved gas. Right, so like how soluble is your gas? How much can that gas be dissolved in your solution? What did we say KH was? This is Henry's constant. And what is P? P is pressure. Okay, so that's just breakdown of Henry's law.
Would it just be pressure? I remember some questions being like partial pressure or something.
Yep, so I believe it's the pressure for that gas, so it would be the partial pressure of that gas. I think so. Because you're only looking at the concentration of this dissolved gas, so you only want the pressure of that gas. Okay. Cool. So then if we were to finish your question, what are we given in, based off of what we know from our formula, what are we given in our question?
Or give you the partial.
Okay, so what's the partial pressure?
I think the maximum area that the road that can be involved in 1,125 milliliters of water.
Okay, great. So this is what we're given for our question, right? We're given the partial pressure, we're given the temperature, we're given the Henry's constant, and we're given the like the want of the question, right? Is that we have 1,125 milliliters of water. We know how many grams of gas can be dissolved in that. Okay, so if we're looking at this, do we have our pressure?
Yeah.
Yes, right, we have our partial pressure. Do we have Henry's constant? Yes, so what do we not have out of our formula? The concentration. What do our units of concentration give us if we were to solve for C?
Well, there.
It- Mole per liter, right? So this is going to be in moles over liter. Okay. So let's just solve for C and see what we get, right? So C, we have 0.025 moles over ATM. And then we're going to multiply it by our partial pressure of 2.46. Yep, so if we have big M, what does that mean? That is moles, right? So this is perfect. So you tell me, right? If we have our molarity and our ATM multiplied by ATM, what happens to our unit?
Oh, just.
Yeah.
They will cancel out, right? So it'll just end up as molarity. So I got a concentration of 0.0615. Capital M. Did you also get that? Okay. Right, so this is the concentration of our gas that can be dissolved. How are we gonna get to grams of that gas? We need moles to grams, right? But what units are we in right now? We're in molarity, which means that this is actually moles over liter. So can we get directly from moles to grams?
From moles per liter.
Right, if we have moles over liters, can we get just to grams? We need the molar mass to get from grams to moles. Right, so if we have what is our gas that it is? Does it get to the molar mass?
It doesn't do.
But it's N2. Okay. So our molar mass refined from the periodic table. So right, we have 14.01 plus 16. So this is going to be 28, 16. 44.02 grams per mole. Absolutely. Yep. Yeah, you'll always be given a formula sheet in a periodic table. Yep. You don't need to memorize that. I just have been looking at the periodic table for far too long. So we have 44.02 grams per mole. So if we want to get to grams, how are we going to solve that? Where does the 44 go? Does it go on the top or the bottom of our fraction? It's going to go on the top. Okay, so what happens to our units? What units are we in now? We're in grams over liter. How do we get to just grams? How do we cancel out the liters?
Can you do conversion between, we're given for that from like certain amount of milliliters?
Yeah, right? So if we look at what we're given, right, this is what we were given in our question. Right, we used our partial pressure. Does Henry's law care about temp? Nope, so we don't, that's just there, tell you what temperature it's at. We're used our Henry's law, but we haven't used this 1,125 milliliters yet, right? Because we have this much water, so for every liter we have, we can dissolve this much, and we have this much. So what is our conversion from milliliters to liters? Divide by 1,000, so we have 1.125 liters, and where does that go? How do we use this? We can multiply it, right? Because if we multiply by 1.125 liters, these liters cancel out. And we're left with 3.045 grams of N2O. If we were to do sig figs, what would that be? Where'd you get 2 from?
So, yeah.
So Henry's law is a constant. When we talk about constants, we can consider those infinitely significant. So any Henry law's constant you don't need to care about. I think what you would look at is your partial pressure and your amount of water. So which one has least amount of sig figs there? Partial pressure, so how many do we need? We need 3, right? This one has 3 sig figs, this one has 4. So my general rule of thumb is that you look at the sig figs at the start of your question. Right, anything that's a constant, ignore that. But like values you're given, look at how many sig figs they all have. This one has 3, this one has 4. Doesn't matter if you're multiplying, dividing, adding, subtracting, just have that many sig figs at the very end. So we'll have 3.0. What do we do to the 4? Round up or down? We can round up, so we have 3.5 grams of N2. That makes sense. Will you do that question? Right, so I think the most important part, and what you'll see a lot throughout Chem 120, is the emphasis of units. Right, sometimes you might not know how to do a question or where to go. But if you write out your units in your question, you're gonna see, okay, my pressures are gonna cancel out. I'm left with molarity. What does molarity mean? What do I have that's also in that same unit that I can use for that one? So I'm a big proponent of making sure you write down all of your units when you're doing any sort of problem. Sometimes I think it just creates a roadmap of what you need to do. That help? Any other questions? Okay, so when we talk about mole fraction, what does that mean? Or what's the symbol for that? Yep, so it's partial moles, so we'll say N of A over the total moles. And your symbol is gonna be like a fancy X. Right, it's like a squiggly X with the line, I don't know. And then you usually just give it the denotation or the subscript for whatever that partial thing you're looking for, which is A, in this case. And if we know moles of A over moles of total, what else do we know? What else does mole fraction tell us? It might not make super sense because it's called the mole fraction. You're like, that's the mole fraction, Allison. But if you have the mole fraction of a gas, you also know the partial pressure of a gas. Or you can at least figure that out if you know the total pressure. Your mole fraction, just to check your answer kind of situation, this has to be greater than 0, but less than 1. It can technically be less than or equal to either one of these. If you only have one gas in the system, then the mole fraction is just whatever the total pressure is, right? So it could be 1. But right, they should be In between, they should be a decimal. They should be less than 1 because it's making up a part of a whole. And then if you have multiple, right, multiple gases, if you have gas A, gas B, and gas C, and then the N of A, the N of B, and the N of C should equal the N total. Right, all of those should equal up. Just simple partial pressure stuff.
I don't understand how the number of moles like relates to the pressure of like a gas. Like how are those two different things related?
Yep. So that goes back to the ideal gas law. So remember what the ideal gas law is? Perfect, right? So PV is going to equal nRT. So if we look at this equation, if I were to tell you that the pressure goes up, what happens to this side?
It directly goes up.
It directly goes up as well. So, right, if this goes up, this has to go up. And inversely, if this goes up, this has to go up. So if I tell you that I'm increasing the moles of gas A, what does that mean for the partial pressure of gas A?
It directly.
That directly goes up as well. So that means that pressure of A goes up as well. Okay. If you think about that in the case of like a balloon, right? You have A, and then you have B and B. Okay. We'll just call those are molecules. A is exerting 3/5 of the pressure on the balloon, right? Because we have 5 total molecules, 3 of them are A. So the pressure of A is 3/5. Okay, so that's exerting a certain amount of pressure. If we added more A to the balloon, now our pressure goes up. Now we have 8, but now how much A do we have? 6/8, right? So we go from 0.6 to 0.75. Right, so this mole fraction here, the pressure that is exerted by A is directly related to the number of moles, right? Because it's the number of collisions that are happening.
But the caveat would be the volume and temperature after remain the same.
The temperature and the volume have to remain the same. Yep. Right, if your number of moles is staying the same and your temperature increases, now your A is just moving faster, right? So your pressure is going to go up if your temperature increases, because now your A is moving faster, it's hitting the wall more frequently. And then if your volume is going down, that's when your pressure increases, right? Because these will have an inverse relationship. So if the volume goes down, now this is closer together, they don't have to move as far before they hit the wall again. Okay, was there a certain question from class that you were looking at, or just this helps a little bit? Okay, perfect. One thing you can look at, right, if you know, you can be given masses of gases that are in the system, right, and then using molar mass of all those gases, you can find out the moles and find out the mole fraction from there. So if you have we can do this question. So we have in a container 12 grams of O2 and 12 grams of oxygen. Wow. 12 grams of O2 and 12 grams of hydrogen are present. What is the mole fraction of H2 in the system? Okay, so what are we going to do first? You have to convert the grams to moles of both the oxygen and the hydrogen. So we'll have 12 grams of oxygen. How do we convert from grams to moles? Molar mass. Does anyone know the molar mass of oxygen? Just one oxygen? 15.999, essentially 16. So what's the molar mass of O2? 32. Perfect. So 1 mole of O2 is 32 grams of O2. And then have 12 grams of hydrogen. So 1 mole of hydrogen, does anyone know what that one is? Yep, 1.01-ish essentially for hydrogen. So what's H2? 2. So now we have the moles of oxygen and the moles of hydrogen. Before you even find the mole fraction, now looking at the number of moles of each of them, should H2 have a high mole fraction or a low mole fraction? It should have a high mole fraction. Why should it have a high mole fraction? There's more moles, right? There's obviously more of this in here, right? You have 5 compared to 0.3, essentially 6 compared to 0.3. So you should get something close to 1, right? So that's a good mental check once you do find what your mole fraction is. So if we want the mole fraction of H2, we're going to take the moles of H2, which is 5.94. And you're going to divide it by the total moles. How do we find the total moles? You have to add them together. We end up with 0.94 as our mole fraction of H2. So does that match our prediction? Yes. Yep. Which I always think is a good thing, right? One thing I always ask myself is, does this answer make sense, right? Does this make sense for what I'm solving for based off of all the other stuff that I've done so far? Or that initial prediction, right? And we predicted that this should be pretty close to 1, and it is. So that's good to know. I feel confident with my answer. Does that help you a bit? Any other questions? Yeah. Yeah, absolutely. Mhm. Okay, so you tell me, what are the different like molecular forces that we have? Intermolecular forces. Mhm. So we have van der Waals or London dispersion forces. Where do we find London dispersion forces? Everywhere, right? All of these have them. Okay, what else do we have? So are these strong or weak? These are very weak. They can get very strong, right? In the sense of like iodine, right? That's I2, it's a dipolar or diprotic atom. Diprotic molecule. So there's 2 iodines bonded to each other. That means it's nonpolar, but it's solid at room temperature because the van der Waals or the London dispersion forces are so strong that it makes it solid, right? So they can have the potential to be pretty strong, but more often than not, they're your weakest molecular force. What else do we have? We have dipole-dipole. When does this happen? Two polar molecules. And when did we say we have a polar molecule? What causes polarity? Perfect, right? So if we have something, oh, I need a polar molecule. If we have something like water, that's a good one. Maybe something like water. And we had another water molecule right next to it. Are there dipole-dipole interactions between them? Yes, there are, right? Because this has a dipole moment pointing this way. This one has a dipole moment pointing this way. So they're lined up so that your partial positive and partial negative are close to each other, and then your partial positive and partial negative. Right, keep going. So it would look like right, something like that, where your partial negative is now close to your partial positive. This is showing your dipole moment. So if we look at the shape of water. What is the electron domain geometry?
Okay.
That's your molecular domain. What is your electron domain?
Or-
Tetrahedral, right? Because tetrahedral is 4, and we have 1, 2, 3, 4 domains, right? So this is a tetrahedral electron domain geometry. Testing you today, what you remember. Right, so you have a tetrahedral electron domain geometry, and you have a bent molecular geometry. Okay. So when we look at the tetrahedral shape, right, I think of this as a tripod, right? So you have 3 feet, I guess, right, pointing down. Your central atom, or the oxygen in this case, is your like where your phone would be, or where the phone part and then the feet part connect. And then right where your phone is would be that last electron domain. So you have the 3, and then you have the last domain up here. That's how I picture it in my head. If you use it, great. Right, so you have 4 different electron domains. We now say that, we'll say this top one and then my thumb are gone. Those are where the lone pairs are. So now we have 2 electron domains, and we have a hydrogen here and a hydrogen here. So I guess in this case, it's gonna look like this, right? What's more electronegative, the hydrogen or the oxygen? The oxygen. So where is our dipole pointing? Towards the oxygen, right? We point towards our more electronegative atom. So this overall up arrow, based on what I showed it, is because if we were to break this down into vectors, this vector and this vector, right, the ones pointing at each other, are going to cancel out. Hydrogens are on the same side. They are going to have the same mass, or the same pull, I guess, or push towards the electron domain. It's not, they have the same electronegativity. But this and this vector are now going to be on top of each other, right? They superimpose. And so overall, this goes away, these create that overall dipole moment, right? And it's always going to point that way. Even if I drew water this way, it still points through that oxygen, right? This one points through this oxygen. Does that make sense where that comes from? Great. It's all just refreshers, right? Okay. I'm gonna move this so I can keep going with my list. Okay, so we have, this would have a dipole-dipole moment. What else does 2 water molecules have? Lovely, right? We have hydrogen bonding. And what is our criteria for hydrogen bonding?
Hydrogen with nitrogen plus
Mhm. Perfect, right? So you have hydrogen bonded to fluorine, hydrogen bonded to oxygen, or hydrogen bonded to nitrogen, right? It has to be directly bonded to the fluorine, the oxygen, or the nitrogen. If you have something like this, right, this is not a hydrogen bond, right? Because the H is not directly attached to that oxygen, right? This is no hydrogen. But in water, the hydrogen is directly bonded to the oxygen.
Is the salt bridge considered an ion? Like for proteins?
No, when we talk about proteins, that's a little bit. We don't talk about, intermolecular forces like that, because those are now amino acids that are really
Okay.
interacting with each other. And the amino acids, right, will have intermolecular forces from the atoms that it makes up. Yep. I just need to zoom in a little bit closer. Great question. Right, so we have our hydrogen bonding. Which one's stronger, your hydrogen bonding or your dipole-dipole? Yep, this is gonna be a stronger dipole-dipole interaction. Right, because a hydrogen bond is still a dipole, right? Your hydrogen has a different electronegativity than your fluorine, your oxygen, or your nitrogen. And that's really like the big three in terms of intermolecular forces. You then can have induced dipoles, depending on what is around that molecule. So if we have just a molecule of oxygen hanging out, right? Is this polar or non-polar? It's non-polar, right? An oxygen bonded to an oxygen, there's no difference in electronegativity. It just has its London dispersion forces, right? It's chilling by itself. If a sodium atom then comes in and says, hi, oxygen, I'm going to be your neighbor now. What happens to your oxygen? What charge does sodium have? Has a positive charge. What is that going to attract? The protons or the electrons? It's going to attract the electrons. So now this oxygen atom here is going to move its electrons closer this way. The electrons in this bond are now going to push a little bit this way. The electrons in this oxygen, right, are now going to say, oh, this is pretty negative. Maybe I just give all of my electrons to this. So now our dipole moment occurs because we have this positive charge close by. Okay, so that's going to cause an induced dipole, right? An ion, so sodium ion is coming by, an ion induced dipole. If over time, right, the sodium atom goes away, we're going to reestablish that nonpolar oxygen atom. Okay, so this is an ion induced dipole. The same thing can happen, but with a polar molecule, right? You can have something like oxygen again, but this time we'll say SH comes by, right, and says, howdy. Is there a difference in electronegativity between sulfur and hydrogen? There is, yep. So which one's more electronegative, the sulfur or the hydrogen? The sulfur is. You would be given values to prove that, but the sulfur is more electronegative. So which one has the partial charge, the sulfur or the hydrogen here? Or I guess which one has the partial negative charge? Sorry, I don't think I finished my sentence. The partial negative is on your sulfur. They both do, Allison, thank you. And your hydrogen is gonna have your partial positive. So out of the oxygens on the left or the right, which one gets the partial positive charge? What is this negative charge gonna do to the electrons in the rightmost oxygen? It's gonna make it positive, right? Do like charges attract or repel? They repel, right? So the electrons are like, oh, I'm a negative charge. This negative charge rolls around, it says flee. So now the electrons are gonna pull this way. So this gets your partial negative, this gets your partial positive. And they're gonna line up like this, right? If you had another oxygen molecule right here, what happens to the rightmost oxygen? That gets the partial positive again, right? You see, it's positive, negative, positive, negative, positive, negative. It lines up like that because now you have a partially induced dipole, right? If this dipole goes away, then our two oxygen atoms, right, reestablish as a nonpolar molecule because now we don't have something polar coming by to induce a dipole. So this is a dipole, induced dipole. Because a dipole comes in to induce a dipole, and if it goes away, then you're back to your nonpolar molecule. Right, this case, a full charge, an ion comes in and induces a dipole, and if it went away, it returned back to its nonpolar, right? So those are your ion induced and dipole induced. Other than that, I think the intermolecular forces, these are the big three of the intermolecular forces.
What is it induced dipole?
This was, so you could either have the ion induced or the dipole induced. That's the induced one. Yep. Right. You're saying you have a nonpolar substance and then something polar comes around to kind of mess that up. Any other questions? Yep.
Dipole induced an ion induced dipole cause a dipole induced dipole? Because I was gonna say how it creates a chain reaction.
Yep. So, right, if there's, right, you're never really just gonna have one oxygen molecule. So this would be a whole bunch of oxygens. This ion-induced dipole would then cause, right, a nearby oxygen to also have a dipole and blah, 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 blah. Yes, that is technically a dipole inducing a dipole, but it's because of the ion. So we say the ion-induced dipole as like it's overarching. I guess if you said that you had like oxygen here and then nitrogen here, and then your ion came over here and caused this to have a dipole, then this would cause this to have a dipole. Then you could say yes, but we're just looking for like what is happening in the solution. It's not that big of a deal. You just need to be able to recognize if it's happening. Anything else?
It's probably super simple. There was a hypothetical question that we have in class.
Mhm.
Do you have one of them?
Yeah, can you just tell me what the eye-clicker question was?
It was. What is the most action water in the 1.7 million of liquid?
Right, you have a mole fraction of water in this.
Yes.
Okay, perfect. So when we look at 1.75 molar glucose, this is telling you that you have, right, molarity. This is you're all good, moles of solute over liters of solution. Okay. Which one's your solute here, your glucose or your water? Solute is your glucose, right? Your solute, your solute is the thing being dissolved. Your solvent is the thing doing the dissolving. Your solution is the overall afterwards, right? So your solute here is your glucose. So you're saying that you have 1.75 moles glucose, right? You get that just directly based off of it being a molarity. Then you have liters of solution. Your solution here is the glucose and the water. If we just have liters, what else are you given in your eye clicker that can get you to grams? Yep. So if we have, right, we can assume that we have 1 liter of solution, right? If you just have liters, you can assume 1 liter. So you have 1 liter of solution. You can say that your solution is just the water. Okay, so how are we going to get to grams of water? Using our density. What's your density for water? Or what was the density given in your class? So you have 1.1 grams over 1 liter. Right, so you have grams here. So you have 1.1 grams, and then you can use your molar mass of water. One liter, 1 mole. You end up with a number. And then you can take this number of moles plus your moles of your glucose, right? Because that's going to be your mole fraction of everything. So you have 0.061 divided by, oh, mental math, 1.811. And that should give you your mole fraction there. That's what I got. Hopefully that was the answer for the clicker. Okay. That makes sense how you would use that. Right, you just need to remember that molarity breaks down into moles over liter, and that's moles of solute over liters of solution. So then if you're given your gram or you're given your density of your solution, then you can use whatever volume you have and then use that to get the number of grams. That grams is essentially water. We can call that for solution, so you can get that moles there and then use your mole fraction from before. Anything else? Alrighty, well, it is 6 o'clock. So we can wrap it up there for today. I'm also the IA for Dr. Bengali, who teaches 107. So if you need a refresher on 107, you're more than welcome to stick around. If not, hopefully this was helpful. Hopefully I see you next week, and then good luck on your homework. And I'll see you in class on Friday. Thank you. Yep. I usually just do this one, and then I make practice problems that I post on Fridays, and then I usually post the solutions by Sundays. So that's just like, it's not me teaching you, but it's just passive extra practice that you can do. And then before exams, I always do a little longer session, at this time, and then I do a Zoom review session beforehand as well. Yep. So in the past, because I've worked with her before, so in the past, she's done a mix of multiple choice and short answer. She told me this semester she might make it all multiple choice to make it easier for me. So plan on both of them, plan on a short answer, right? I always do my questions as short answer. And sometimes I do like a fill in the blank kind of thing. But most of the questions we'll do here are short answer. You can do a short answer, you can do a multiple choice. So train harder, work smarter, right? Or train harder, test smarter. But I think it's gonna be all multiple choice this semester. Yeah. Um, 107 moves much quicker because they cover a little bit of Chem 120 at the very end, but they don't go into like they only talk a little bit about acids and bases and like ice tables, but not to the depth that you are going to. So 107 is more of like a condensed scratch the surface kind of sort class, and then 119 and 120 have more time to talk about each of the topics and talk a little bit more about not necessarily the shiny or they talk a little bit more about the shiny stuff. 107 is more like highlight reel, right? And then 119 and 120 you can dig a little deeper because you just have more time to cover the whole course.
Is there anything missing for the books as opposed to one?
I don't think so. I think if you take 107 to 120, you get what you need out of 107, right? That's like enough of 119 to make you succeed in 120. Yeah. I think you get more in 119, but the more that you get is not necessarily what's going to help you with 120. Does that make sense? Right, you get a little bit more formulas or like you talk about a little bit more stuff, but that's just like, oh yeah, we can talk about it because we have time and not, this is like really important. Yeah, absolutely.